In this second equilibrium constant video, I'm going to deal with the type of calculations that you often get in A-level exams. So we'll start with this question. It's a classic esterification reaction, and we are told that 0.2 moles of ethanoic acid was reacted with 0.1 moles of ethanol in the presence of an acid catalyst and allowed to reach equilibrium. The total volume of the mixture was 200 cm cubed, so the combined volume of these two chemicals was 200. At equilibrium, it was shown that 0.115 moles of ethanoic acid were present. Calculate Kc. So the first thing we're going to do is we're going to write underneath the chemicals the information from the question. So I'm putting the initial I there, and these are going to stand for the initial moles. So what's the initial moles of ethanoic acid? It's 0.2. Initial moles of ethanol, 0.1. Now before these get the chance to react, the initial moles of ester will be 0 and water would be 0 as well. So the next thing we're going to do is we're going to look at the equilibrium. So I'm going to miss some space here, leave some space, and I'm going to put E there to stand for equilibrium moles. So the equilibrium moles of ethanoic acid is 0.115. So from that we can see that if we started with 0.2 and we've got 0.115 left, then the difference is obviously how much is reacted. So we could put a C there, that's the change in moles. So we've got the change in moles is going to be 0.085. Now we've established how many moles of acid have reacted, we can then feed this information into the rest of the reaction. So the mole ratio between these two chemicals is 1:1. So therefore, if 0.085 moles of acid has reacted, the same number of moles has reacted of the alcohol. So the change of this is going to be 0.085. Which means that at equilibrium, if you started with that, that's how many have reacted, then this is going to be the difference, which is 0.015. So if we look at the products now, what's going to be the change in the moles of the products? Well, these have gone down by 0.085 moles, so the minus sign I've included there. Now because the mole ratio between these and the products is 1:1 as well, well these will go up by this many moles. So this is going to go up by 0.085, as will this, 0.085. So that means that obviously if you started with 0 and it's gone up by that many, well that's how many you've got at equilibrium. Now, the next thing is we need to turn these moles into concentrations. Remember the Kc expression, Kc is a measure of the equilibrium concentrations of products over reactants. Now we've got moles at the moment, so we need to turn these into concentrations. So I'll just put an extra row here, so E conc. How do you work out concentration? Moles divided by volume, so we were given the volume somewhere in the question, 200 cm cubed, which is of course 0.2 decimeters cubed. We need to work in decimeters cubed for concentration, and so the equilibrium concentration will be 0.115 divided by 0.2, 0.015 divided by 0.2, 0.085 divided by 0.2, and the same there. So we're ready to calculate Kc now because we've got all the equilibrium concentrations. So if we write down the expression for Kc, so it's equilibrium concentration of the ester CH3COC2H5 times the water concentration all over the acid concentration. No powers needed here because everything's balanced with a 1. So that's going to be 0.425 multiplied by 0.425 all over 0.575 multiplied by 0.075. And that gives us a numerical value for Kc of 4.19 to 3 significant figures. In terms of units, moles per decimeter cubed, squared on the top and squared on the bottom, and so it actually has no units. So we'll look at this one now. The wording's a little bit different. They sometimes like to ask things in a sort of more obscure way to really test people's understanding. Essentially though, the method's still the same. So we've got at 300 Kelvin, temperature of 300 Kelvin, 1 mole of N2O4 is 20% dissociated. And we're told that the flask that it's carried out in has a volume of 2 decimeters cubed. Calculate Kc. So initial would be 1.0, and initially you wouldn't have any of that. At equilibrium, you would have, if it's 20% dissociated, that means 20% of it has broken off or split up, and so there'd be 80% left. So 80% of 1 mole is 0.8 moles. So we can see now that the change is obviously a drop of 0.2 moles. So if the change of this is 0.2 moles, well, how many moles of NO2 would be produced? So where we look at the mole ratio, 1 mole of that makes 2 of those, and so 0.2 would make 0.4. Remember, this goes down, this goes up. And so if you start at 0, you've made 0.4, you've got 0.4. So these are the equilibrium moles. Turn it into concentrations now, and we divide that by the volume. So that would be 0.8 over 2, 0.4 over 2, that's obviously 0.4, and that's obviously 0.2. The Kc expression for this equilibrium is the concentration at equilibrium of NO2 squared, is that 2 there, divided by the equilibrium concentration of N2O4, so it'll be 0.2, the equilibrium concentration squared over 0.4, and that comes out at 0.1. Let's look at the units now. We've got moles per decimeter cubed squared divided by moles per decimeter cubed. So this moles per decimeter cubed will cancel. We'll be left with 1 on the top, so it's just moles per decimeter cubed in this case.